At medyo may pagka-technical yung ano natin right now. But in the end, so aside from the recording, maglalagay din ako nung ano sa both section ng mga notes, parang summary ng mga diniscuss natin. So at least pwede niyong tingnan yun. And I will make available also yung ano natin, yung material para at least may makita kayo habang meron kayong material habang nanonood kayo uli ng record. Okay? So I will try to do it by siguro tomorrow morning dito sa US. So we have this what we call introduction last time no electrochemistry, and as you would know, meron tayong tinatawag na review session about doon sa chemistry. Okay? So what we're going to do now, we're going to focus on that three methods that is usually being used in most fields. Okay? Or they have a lot of application. Teka lang. I-share ko kasi. So the first one that we have, okay, is yung tinatawag nating potentiometry. Okay? So when we're talking about these potentiometric methods, it's based on the measurement of this what we call potential. So ang ano dito, ang pinaka-classic example of potentiometric method ay yung siguro familiar yung lahat sa pH meter. Okay? So it measures the potential, measure the potential of the electrochemical cells in the absence of appreciable current. So it's just look at the potential. So we could say it really looks at the activity, kung ano man yung ion na minomonitor natin. So if it's a pH meter, ano yung ion? Okay? It's usually the hydrogen ion. Now, if we're going to look at the pH meter, titingnan natin yung parang isang probe lang siya. But if you're going to look at it, if you look into the details, okay, they have these three basic components. Yung sa classic lab nga, okay, kasi ngayon karamihan ng mga pH meter, yung parang katulad lang nito. I don't know if you can see my writing pen. All you need to do is just dip it and then it will give you the pH, what we call level or pH value. But deep inside there, meron siyang reference electrode, indicator electrode, at saka yung tinatawag nating potential measuring device. Okay? So if we go one by one, dito sa mga component na to, yung reference electrode, yan yung parang reference na ginagamit for potential measurement. And we will go on to discuss some of these reference electrode as we go on. Okay? And then if we have this indicator electrode, dyan natin nilalagay yung species of interest. Mini-measure natin dyan. Tapos yung huli yung potential measuring device. So if we're going to look at the cell diagram, so this is still part of the electrochemical cell. So yung titingnan natin, meron kang reference electrode that gives the potential of the reference, and then yung salt bridge, so yan yung ano yung EJ, liquid junction potential. And then yung analyte solutions, yan yung sample mo, at saka yung indicator electrode. So if you're going to look at this component, maaring ito yung classic na pH meter. Okay? So you have this probe or the electrodes dip in the analyte solution. So meron nandyan yung tinatawag nating reference electrode, yung indicator electrode, and then we have the salt bridge. Okay? So dyan natin makikita yung potential na makukuha niya is just equals to this side minus this side. Because we could say this is your cathode and this is your anode side. So, kaya nag-review tayo because this is still an application doon sa tinatawag nating electrochemical cell. And when we have this reference electrode, we need only one electrode of this system that acts as a reference against which the potential measurements can be made. So it's just being used like a relative comparison. So yan yung point of reference natin. Okay? And for you to be a reference electrode, you have to meet these characteristics. So since you are using it for relative comparison, it should have a known or fixed potential. Ayaw mo mabago-bago yun kasi mababago-bago din yung reading mo. Okay? The response of it must be what we call constant. Okay? I remember this afternoon, we have an experiment on potentiometry. So they're measuring this fluoride ion. So we use a special type of potentiometric application. So I told my students, the higher the concentration of your fluoride, the more constant will be the response. So if you're using a blank there, that's just what we call distilled water because they don't have the patient to wait until the words table come up or showed in the what we call the meter. So I just told them that's how it is. If you don't have anything there, the response will not be constant. Okay? So kasi yun yung characteristic ng reference electrode. And then insensitive to the composition of solution under study. So kung ano yung target niya, yun lang yung titingnan niya. And then obeys the Nernst equation, and then it is reversible. Now, if you're going to look at some of the reference electrode, okay, so you have here the Columnal electrode, the saturated electrode, the silver-silver chloride electrode, and the saturated silver-silver chloride. And if you're going to look at it, some of them are what we call, they have a constant response, and some of them we could say are a little bit, no, not a little bit, they're changing, but not too much. Okay, but it is, we could say, understandable because at higher pH, the activity of the ions, for instance, here the hydrogen that you're looking for is also changing. So malamang magkaroon din ng pagbabago doon sa reference electrode. So as you could see here, they're okay at this temperature, and then you increase the temperature or the temperature become higher. So bumababa yung electrode potential niya. Okay? And then the same thing with this, what we call the 3.5 molar calomel. In fact, you could say that as the temperature increases, the potential, okay, doon sa reference electrode mo, nagdi-decrease. Okay, but usually we only use this at room temperature. Unless you want to monitor an activity, like let's say at a much higher temperature. So you have to take that into consideration. So ano yung common na reference electrode na ginagamit, especially sa potentiometry? So one of the things that they use is this Columnal electrode. Okay. Now in the Columnal electrode, there's a mercury that is in contact with the mercury chloride and KCl. Now, usually ang tawag sa kanya is SCE, which is saturated Columnal electrode, and this is very widely used. Now, if you're going to look at the half cell reaction that is happening here, so ito yung nagpo-form. So yung mercury with mercury 2+, okay, and what we call in a KCl. So if you're going to look at the reaction there, so this is the reduction reaction. And the thing that you have here, your response, the response of the saturated Columnal electrode depends on the chloride ion. So you will see always that there's some sort of a plug in this type of electrode. Okay, so yan yung pinaka, we could say one of the most common one, but the one that I usually use here is the silver-silver chloride electrode, which is like this. Okay, so this is the most widely used reference electrode system, and this is a silver electrode in KCl that is saturated with silver chloride. So if you're going to look at the half cell reaction that happened here, okay, so this is the reduction of a silver ion to solid silver. Now, the advantage of this silver chloride electrode compared to the saturated columnar electrode is you can use it even at high temperature. Remember in the previous slide, as the temperature increases, yung potential ng SCE nagdi-decrease. Okay? Now, although it has that advantage, meron din tong disadvantage. Okay? Silver would react with more ions. I don't know if you're familiar yung titration that involves silver. What do you call that titration? I think one of the common thing that they ask in the board exam, what type of titration is that? Naalala niyo yun sa 32? Yung tinatawag na argentometric titration. Okay? So, you know that there's a lot of this argentometric titration. I don't know if you still remember the Moore method, the Bolhard, the Fahans method. I'm not going to discuss that, but those are just common, what we call argentometric titration. And I know when I was taking my 32, that was tackled. So I think even now, I expect that it's being tackled because in our part here, we also discuss about this argentometric titration. Okay, the one that always gives you some souvenir for a week. Pag naano ka ng silver nitrate, nahawakan mo with your bare hands. Now, the precautions that you have to use in the reference electrode is you need to keep the level of solutions in reference electrode above level in the analyte solution. So dapat nakalubog, okay, doon sa analyte solution mo. And as much as possible, you need to prevent the flow of the analyte solution into the reference electrode because ang mangyayari dito, maapektuhan yung junction. It can result in the flagging of electrons at the junction, which gives you an erratic behavior. Okay, so we could say that's the most common reference electrode. Pero meron pa rin tayong yung later on yung of the different. But I think this is the one that you usually use, either SCE or the silver chloride electrode. Okay. Now, in terms of the indicator electrodes, you use it to detect or respond to the presence of the analyte. And this is the one that you have on this side, the right side of the cell's notation. So there are three common types. We have these metallic indicator electrodes, the membrane indicator electrodes, and the molecular selective electrode. Okay, so if you're going to look at these indicator electrodes, the one that we have here, okay, so usually makikita mo, depende dun sa application, depende dun anong indicator electrode yung gagamitin mo. Okay, so if you look at this indicator electrode, the potential of the indicator electrode in a potentiometric electrochemical cell is proportional to the concentration of the analyte. Kaya nga, yun yung main function niya. Detects or responds to the presence of the analyte. Okay? So, if we're going to look at the metallic electrode, meron pa yung tinatawag nating 4 main types. Okay? So, yung parang metallic electrode of the first kind, metallic electrode of the second kind, or metallic electrode of the third kind. I'm not sure if you're familiar of that first kind, second kind, or third kind. I think the only one I remember is there's a movie that's called Close Encounter of the third kind. Okay, so when we're talking about metallic electrodes of the first kind, it involves single what we call reaction. Okay, so in the electrodes, this type of electrodes of the first kind, usually your metallic indicator electrode, it is in contact directly with the metal in a solution containing the ions. Okay, so makikita rin dito yung detection of the cathode derived from the metal used in the electrode. So yung ano dito, yung electrode mo, Same kind doon sa analyte mo. Use of copper electrode to detect the copper 2+ in the solution. Okay? So if you're going to look at the reaction that you have here, so you have a copper 2+ and then 2 electrons, that's the reduction of copper 2+ to give you metallic copper. So if you have the indicator electrode, it gives you the direct measure of your copper 2+. So pag meron ka doon, makikita mo agad yung activity ng copper mo between the two. So you just use this parang pH, but instead of a hydrogen, you look at the species that you're looking for, which in this case is the copper. Okay? The power of the copper. So yan yung tinatawag nating first kind. So these are metallic electrode metallic indicators, electrodes in which a metal is in contact with the solution containing its ions. So yan yung metallic electrodes of the first kind. Now there are some problems associated with it. Okay, it's not very selective. Okay, although ang ini-interact nitong metallic electrode ay yung mismong analyte niya, but it can also interact with other analyte. Hindi siya masyadong selective. And then many can only be used at neutral pH because you know what happened at different pH. Okay, some of the metals will be dissolved in, let's say, acidic solution. Okay, and then you can also have to take into consideration that some metals readily oxidize. Okay, and they found out that some of these hard metals like Fe, chromium, cobalt, and nickel, they don't give you reproducible results, and that's going to be questionable. Yung pabago-bago yung reading. Tapos pareho lang yung sample na mini-measure mo. Okay, and the power of the X, so that's whatever the metal that you have versus the activity, differs significantly and irregularly from the theory. So yun yung masama dito sa metallic electrodes of the first kind. Okay? Now doon naman sa kasunod, so meron tayong first kind. So yung kasunod naman, the metallic electrodes of the second kind. So what does it mean? So you have a metallic electrodes of the second kind when the potential of an electrode of the first kind responds to the potential of another ion that is in equilibrium with your Mn+. Okay, so here usually since your metal ion is always what? A positive sign, a cation. So if you have the second kind, it will detect the anion that will interact with your metal ion from the electrode. And in this case, usually the anion forms a precipitate or stable complex with metal ion. So your angiometric titration, what's the common ion that when you react with silver ion, it will give you a precipitate. So usually it is the chloride, right? So meron kang, let's say, a silver electrode here, and it can detect yung chloride. So yan yung metallic electrodes of the second kind. So if you're going to look at the reaction, so if you have a silver chloride reacting with electron, so mag-produce yan ng silver metal tsaka chloride. Okay, so the indicator there who gives a direct measure of your chloride. Okay, so ang nangyayari dito, yung activity na nakukuha mo, okay, is being related doon sa interaction ng silver chloride na nagproduce ng chloride. Now, another example of the second kind ay yung tinatawag nating mercury electrode reacting with EDTA. Okay, so you know EDTA is what? A chelate. Okay, so usually it's not only mercury that it will chelate. It will chelate in most of these other known metals. Okay, but what they found out, if you have a mercury electrode, so that's just similar to your saturated Columnal electrode, they can interact with the EDTA. So ang na-measure doon ay yung presence ng EDTA. Okay? So the hap reaction that you have there, your EDTA, okay, undergoing reduction to produce silver ion and the EDTA 4- na ion. And it gives you a corresponding potential. So yan yung, we could say, two common kinds of this so-called indicator electrode. Okay? So pwede natin isama dito, even though we use it as reference electrode, both the silver chloride electrode tsaka yung tinatawag natin Columnal Electrode. Kasi ito yung ginamit natin eh. That's a silver chloride electrode. And this one, that's your Columnal Electrode. Okay? Now, we have the other one, yung tinatawag nating third kind. So the metallic electrodes of the third kind. Okay? So if you're going to look at this type of this, what we call the electrode, okay? These are the metal electrodes that responds to a different cation. So kung meron kang silver electrode, magre-respond siya hindi doon sa silver or doon sa chloride, kundi sa iba pang tinatawag nating cation. Okay? And you can link it to a cation by an intermediate reaction. So you already saw the detection of EDTA by the mercury electrode. That's the second kind. And you can make it to detect other cations because as I told you, yung EDTA, nagbabind siya sa iba pang metal. And when that happens, it can affect the concentration of the EDTA ion that form. So for instance, may calcium doon sa solution mo. It can complex with your EDTA. So parang nagko-compete siya doon sa binding ng EDTA sa mercury electrode. So invest na yung EDTA, mapupunta lang doon sa mercury electrode. Some of them will bind with the calcium ion. Okay? So ang mangyari, may competing reaction. So yung Y 4+ na nagpo-form, hindi lamang yang galing doon sa electrode na mercury, kundi doon sa calcium. Okay? Now, if you're going to look at this, both the activity of your EDTA ion, tsaka yung electrode indicator mo, it changes with respect to the activity of your calcium 2+. Okay? So the last type that we have here, so meron tayong first kind, second kind, third kind. Yung last type na meron tayo ay yung tinatawag na metallic redox indicator. Okay? So these metallic electrodes, these types of what we call the metallic electrode, they serve as a source of or as a sink for electrons in other redox reactions. Okay? So in this case, yung electrode mo, it comes from the so-called inert metals, platinum, gold, palladium, yung tinatawag na nating noble metals because they don't react, right? Yun yung mga jewelry na mga metal. They don't usually react right away. Inert usually sila, and usually the platinum electrode is one of the most commonly used indicator electrode. In fact, that's the one that they use if your substance don't, your given element don't have the solid state, gaya nung hydrogen, okay, forming into hydrogen ion, hydrogen gas to hydrogen ion. So it used to detect oxidation, redox reaction in a given solution. And as I said, it acts as either an electron source or a sink for electrons. So the classic example we can do here is this platinum electrode that is detected by Ce3+. So there's a reaction there of Ce4+ reacting with electron to give you Ce3 plus. So usually we do it using titration. This one reacting with Fe2 plus. Okay? So yung Fe2 plus mako-convert siya sa Fe3 plus. Okay? And sometimes we use a platinum electrode, but usually we only have one because it's not really commonly used. Ang ginagamit na namin yung conductiometric electrode namin. Okay? So if you have this type of metallic redox reaction, your potential or the indicator potential responds to Ce4 plus. And it has some problem, especially with regards to the electron transport processes. Okay? So when it is in inert electrodes, it's just, we could say, a one-way reaction. It's not reversible. And they do not respond predictably to one half of the reaction in your what we call reduction potential. So yan yung we could say first type on yung tinatawag nating metallic electrodes. Okay? Now, the next one that we have is the so-called membrane indicator electrodes. So when we're talking about these membrane indicator electrodes, okay, this is, we could say, the general information that we have about them. So these are electrodes that is based on the termination of cations or anions by selective absorption of these cations to a membrane surface. So ito yung tinatawag nating ISE, ion selective electrode. And that's what my student used this afternoon when we try to determine fluoride in different mouthwash and toothpaste samples. Okay. Now, the desired properties of ion selective electrodes, as much as possible, hindi siya soluble. Ayaw mo yung pagbaba mo nung ISE, kita mo nawawala o ano nangyari. So, natutunaw, ayaw mo mangyari yun. As much as possible, they will remain undissolved. Okay? So the membrane will not dissolve in solution during the measurement. So how do they do that? They use either silica, polymers, or low solubility in organic compounds like silver chloride. Okay? And then another property is you need to have some electrical conductivity. Okay? And the most importantly, it selectively binds doon sa ion of interest mo. So ang nangyayari kasi dito, pag nag-bind, doon mag-create no parang electron conductivity. That's why you need it to have some electron conductivity para makita yung changes once nag-bind doon sa target of interest mo. Okay? And what do you think the classic membrane indicator electrodes? Anyone? Ano sa tingin niyo yung classic na type na electrons nito? And I hope you have used this already. Ito yung tinatawag na pH electrode. Okay, yung pH meter. So that's the most common example of ISE. I don't know if you noticed it. Yung glass membrane na meron kayo dito, it's so thin. That's why as much as possible, don't hit it with, ano tawag dun? Yung magnetic bar. Okay. Has everyone used a pH meter? Lahat ba nandito nakagamit na ng pH meter? Even yung simple one, kapag may aquarium kayo, makikita nyo yung tinatawag na pH level doon sa water ng aquarium niyo. As you can see, meron din siyang parang manipis. Manipis yun eh. Okay? And it was just told to me doon sa lab namin, bakit daw every week nag-order, may isang grad student nag-order lagi ng pH meter. Okay? Tapos nung pinakita kung paano niya ginagamit yung pH meter, so may sample. Tapos nakita nung advisor, diretso doon sa magnetic bar, itong bulb na to, kaya laging nababasag. Okay? sometimes my students there will say, Professor, why is the pH not changing? And then I told them, maybe you broken, okay, the glass membrane. Kasi dyan yung nagkakaroon yung interaction eh. And usually, di ba, minsan, meron yung cover to the point that if you don't know how to use it, you dip your pH meter with the cover. At tapos magtataka ka, bakit walang reading? Or hindi nagbabago yung reading? Because your sample cannot go to that what we call glass membrane. Okay, diyan nagbabind kasi yung H plus mo. Okay, so the typical pH electrode system is shown here. So pwedeng yung dalawahan o yung isahan. Okay, but whatever it is, you could see that one of them would always have the thin pH glass membrane. So in the two reference electrodes here, you have one saturated columnal electrode and one silver-silver chloride inside the membrane. Okay, and in what we call the pH sensing element that you have there is the glass tip of your silver chloride electrode. Because if you look what is happening, paano ba na-measure yung pH? Okay, it has something to do with the presence of your H plus. So ang nangyayari usually, glass is made up of what? Silica. So meron kang glass membrane doon. So doon sa silica mo, meron kang fixed hydrogen ion or fixed activity ng hydrogen ion. Now, doon sa sample mo, variable yung H plus mo. So what they do is they look at the difference doon sa potential ng nasa glass surface at doon sa sample mo. Okay, so at each membrane solvent interface, a small local potential develops. So kapag hindi sila pareho, okay, that's where potential comes in. It develops due to the preferential absorption of H plus into the glass surface. At when you have that, okay, mapapalo pa rin dito yung tinatawag nating cell notation that we have. pH as determined by formation of the boundary potential across the glass membrane. So meron silang difference. At yung difference na yun, yung nagde-develop ng potential that gives you the corresponding activity of the H plus doon sa sample. Okay? So you might see it here, your saturated columnal electrode, that's your reference electrode. At doon sa glass electrode mo, where you have your silver chloride electrode, ito yung nangyayari doon. So parang reference 1, reference electrode 1 and reference electrode 2. But if you're going to look at this, it's just looking at the difference between the concentration or activity of your hydrogen doon sa glass membrane at doon sa labas. Okay? So yun yung, we could say, basis how you measure pH. Of course, there's always an error. Okay? Ano yung number one rule kapag may pH meter ka? As much as possible, you don't want it to dry up. Right? So as much as possible, saan mo siya ilalagay? Sa isang salt solution. You don't want it to dry up because it will give you an error. And also, you don't want it to be placed in a too much acid or a too much acidic condition because you have this term na alkali error. So ano nangyayari? Okay lang nangyayari itong alkali error mo when you put it in a high pH. So kapag high pH ka, wala kang H+. So usually, anong merong ion kapag high pH? Especially yung source ng ano mo, base mo ay either what? KOH or NaOH. So at high pH, you have a very low activity of your hydrogen because the one that you have there is either Na plus or K plus kung saan man nanggaling yung base mo. So amount of Na plus and K plus binding is significant. So ano nangyayari dito? It increases the apparent amount of your bound H plus. Okay? So itong reading na meron dito, ito yung different brand ng pH meter at different condition. So look at them. Okay, so A and B, this is, we could say, at low pH. Corning 0.15. So if it's in H2SO4, ito yung reading niya. If it's HCl, dito yung reading niya. Now, if it's Corning, the same Corning, but you have 1 molar NaCl, so ito. If it's the Beckman, okay, dito banda. Now, kapag yung ibang type, 1 molar, so iba-iba yung reading ng given electrode. Okay, or as what we call caused by the so-called alkali electrode. Now, we could say this is your alkali error. Ito naman yung tinatawag nating acidic error. This is just the same figure. So acidic error, that's errors at low pH. Okay, because yun yung acidic, di ba? And it can give you readings that are too high. Now, they still don't know the exact cause of this, but they usually observe it happen when the pH is more or equal to 0.5. Okay. Now, another thing that you can consider here is the glass electrode for other hot ions. Kasi hindi lang naman pH electrode eh. So, you can change the composition of the glass membrane. So, instead of your silicate, pwede mo gamitin yung aluminate tsaka borate in glass. And both of them would enhance the binding for ions other than pH+. Pag yan yung materials na meron ka. Okay? So yan yung, we could say, some of the errors that you can have from having high pH or low pH. And then we have another type. Ito yung ginamit namin kanina, yung tinatawag na crystalline membrane electrode. Okay? So classic example that we have is a fluorite electrode. So you have your lanthanum fluoride crystals doped with europium fluoride. Though the mechanism is similar to the pH electrode where you develop potential at the two interface like here. So meron ka na naman peaks na concentration or activity ng ion mo at dito na nagbabago based on your analyte solution. So if you're going to look what is happening there, so doon sa membrane surface, you have lanthanum fluoride producing lanthanum fluoride plus and plus F minus na pwedeng mag-interact or manggaling doon sa solution mo. So the side of the membrane with the lower activity of the fluoride becomes positive relative, okay, to the other surface. And then there's another kind that they have, yung tinatawag nating liquid membrane electrode. I have not experienced using this one. Okay, so this is still a membrane type, but usually you have this so-called organic liquid. Why do they use organic liquid? Kasi hindi siya soluble doon sa sample mo, that is usually aqueous. Okay, and this organic liquid would be held by porous disc between the aqueous reference solution and the aqueous sample solution. And the membrane has the ability to selectively bind ions of interest. Okay? So example na meron sila dito ay yung membrane electrode na nakakabit sa silver-silver chloride. So it has this electrode body, and then inside it they have this internal electrolyte. And this is where the ion selective membrane would go in. So ang ano nito is what we call calcium dialkyl phosphate. That's the liquid membrane electrodes. And what happened at the solution or the membrane interface, this is the one that is happening. At nababago siya based doon sa concentration ng calcium ion mo doon sa solution or sa sample na mini-measure mo. And then the side of the membrane with the lower activity calcium ion becomes negative relative to the other surface. And you can use it to design your own what we call ion selective electrode. Okay, so they usually use the liquid membrane electrode because if you're going to look at this, ito lang yun eh. So all you need to do is whatever's your target ion, gamitin mo lang, lagyan mo lang yung tinatawag na electrolyte doon. And then you have the ion selective membrane there. Okay, so you can design either for cation and anion, the one that you use as cation exchangers or anion exchangers. And usually, okay, they found it to be useful. Especially most of these cations, you use it what? To measure the level that you have in your body. Yun yung parang application itong method na to eh. So if you want to determine calcium ion, okay, so you can develop the liquid membrane and then you can test how it is being interfered by other cation. Okay, and then you can use a BF4 minus tetrafluoride, and then you have the nitrate, the perchlorate, and then the K plus. Or if you want to use water hardness, you have the both calcium and magnesium. But as you could see, you have to take into consideration doon sa interference na magagaling doon sa ions na present doon sa solution mo. Okay? Now, the other thing that they use is the so-called molecular selective electrodes. So instead na ions, ang ginagawa nila ay for a particular molecule. So kung meron tayong ISE, ito yung MSE. Okay? But this is usually limited to those molecules that are what we call in the gas form. So typically, it's based on these ion selective electrodes surrounded by the electrolyte solution. So the activity of the ions measured as affected by the dissolved gas. So ganito yung setup niya. Again, nandun pa rin yung silver chloride electrode. Okay, so meron kang parang tinatawag na internal solution. A sodium bicarbonate or a sodium chloride. So meron kang glass electrode doon, may glass membrane. Tapos yung internal solution ng glass electrode at nandoon yung gas permeable membrane mo. So when the gas effuses through the membrane, so you will see there, oh, there's a CO2 in the external solution, in the membrane pores, and the internal solution. And what happened? Since meron kang bicarbonate doon, yung CO2 mo mag-react with water to produce bicarbonate ion and an H+. And this can be detected by your ISE. So any changes that you have there, malalaman kung marirelate mo doon sa amount ng CO2. And the common one, not really the common, the one that I have what we could use is this enzyme electrode, the biocatalytic membrane electrode. Ang approach dito, i-immobilize mo yung enzyme doon sa system. And usually this enzyme would act what? A certain target or a certain molecule. So the enzyme would convert the given molecular analyte into a species that can measure electrochemically. Yung way nga nung pag-ano dati ng sugar membrane, they put glucose oxidase. Because ang nangyari doon, if glucose comes in, the glucose oxidase will convert it. Okay? And in their conversion, there is some electrical signal that is associated to the amount of the glucose that was act upon by the glucose oxidase. Okay? So parang meron kang enzyme substrate. So they have here what we know so far, yung H+, meron kang pH electrode, CO2 yung gas sensing electrode. Ammonium ion, you can have this ion selective electrode. But if you have a urea enzyme electrode, so ano yung enzyme na nag-act sa urea? Di ba usually lahat ng enzyme nag-end sa ACE. So what you have there is you immobilize urease in the protective membrane. Okay? So either you have an ion selective electrode or a gas electrode. Okay? So i-immobilize mo doon sa protective membrane yung enzyme. So what happened? So urease would act with urea. So ano mangyayari? In the presence of the enzyme urease, your urea is hydrolyzed to give ammonium ion and H+. So i-connect mo siya either doon sa pH electrode na magdi-detect ng H+ or ammonium ion electrode na magdi-detect ng ammonia. So kung gaano kadami yung urea mo, ganun din kadami nung ammonia or H+ na magpo-form. So you monitor the amount of ammonia that is produced using the ammonia gas sensing electrode. Okay? So yan yung maganda doon sa paggawa ng research sa mga electrode. I would say sky is the limit kung gusto mong i-develop, okay? Or mag-develop ka ng sensor mo using this one. But this is just one field. Okay, so we just covered 1/3 nung tinatawag nating electroanalytical. And where do we apply it? Well, you can measure the pH or you can measure some ions of importance. So the experience that we have today, we determine fluoride doon sa mouthwash tsaka toothpaste samples. We also measured the fluoride in some of these water systems because we use this fluoride as a fluoridation system. So question, before we go to the next one. The next one is the most, we could say, the one that's not common. Even I has limited exposure to the next one. So this is the potentiometric method. And if you're going to look at some of these example, ito yung meron siya. So nandiyan na lahat yung electrodes, yung reference siya kayong indicator electrode. And usually when you calibrate it, ito yung reading na makukuha mo. And they're usually small now. So that's potentiometry. Now the next one that we have, if no one have any question, itong colummetric. And to tell you frankly, I never experienced how to do colummetric. Okay. There's an instrument on it, a very old one, but I don't know how to operate it. That's why I never used that one. Okay. Now in the colummetry, so it's not a color, okay? It's a COULO. Hindi yan yung colorimetric, iba din yun. So in colummetry, so that's based on coulomb, which is the unit of charge. So it's an electrical method based on the quantitative redox of the analyte. So what it do is measure the amount of the analyte by measuring the amount of current and time to complete the reaction. So the charge here is just equals to the current times time. Okay, so this is what we call an electrolytic method. What does it mean? You need to apply power. Are you familiar with soldering? Yung parang nag-aano ka?
Yes. Yes.
Okay, so that's an example of the electrolytic method. Kasi ang ano doon, di ba? Mag-apply ka ng current, tapos the longer the time, the more charge that you have, the more materials that you will get kapag nagsosolder ka. Okay? Now, yung technique na ginagamit nila dito ay yung tinatawag na colummetric titration of the chloride. So they use the silver electrode to produce silver ion. Okay? So yung silver solid mo, i-oxidize yun to silver ion. Tapos itatitrate mo yun doon sa chloride. So magkakaroon ka ng precipitate. So ang ano nga dito, this is a second, indicator electrode of the second kind. Okay? Or not really the second kind. Ang ibig sabihin dito, yung silver ion na magpo-form, meron kang second electrode. So this is different from potentiometry. So if you're going to look how it looks like, parang ganito. Okay? So meron kang generator electrode, so steering bar. So kung ano yung mag-generate doon, i-measure ng second electrode. Okay? So you only get complete circuit when your silver ion exists in solution. So kapag hindi mo na-convert yung silver mo, silver metal to silver ion, walang nangyayaring reaction. Okay? So it only occurs after all the chloride is consumed. So you're measuring here the amount of current and time required for the complete reaction. And then you can determine the silver, the chloride ion, the amount of the chloride ion. And if you're going to look at the reaction that you have here, so you have here a negative charge, Q. Okay, so this is based on the measurement on the amount of electricity or charge in coulombs required to convert the analyte to a different oxidation state. Okay, I don't know if you know this thing, basic equation, charge equals to current times time. Now for the variable current with time, so you could say there, okay, the current is equal to the change in the time. So the relative charge that you have to the moles of passing of electrons passing electrode by Faraday constant. So Faraday constants, that's the charge in 1 mole of electron. Some books says 19,485, some books says 19,490, some books says 96,500, 96,500. So if you know the moles of the electrons that's produced, you can determine the stoichiometry of the half cell reaction. Okay, so it gives the number of moles of the analyte generated or consumed. So this is really an electrolytic method. Now there are two types of colorimetric. Meron tayong tinatawag na amperostatic and potentiostatic. Now, the amperostatic is the most common among the two because that's your colorimetric titration. Now, there's a fundamental requirements for both methods. Ito yung tinatawag na 100% current efficiency. Okay? So what does it mean? All the electrons go to participate in the desired electrochemical process. If not, then it takes more current. And what happened if you have more current? Because you want to relate the current with the amount of the analyte. Kaya tinatawag na 100 current efficiency. So for every current that you have, there's an associated amount of analyte. So kapag mas mataas yung current, okay, pwedeng ma-overestimate yung amount ng analyte mo. Okay? Now, in the amperostatic method, which is just colorimetric titration, the basics that you have there is just like a typical titration. Titration of the analyte in solution by using colorimetry at constant current. So, imagine your pH meter, papalitan mo nung ibang electrode. Okay? So, it generates a known quantity of a titrant electrochemically. So, you're going to do what we call set the potential by the contents of the cell. So when you have this reaction, silver to silver ion, for the precipitation of the titration of chloride, to detect the endpoint, you have to use another electrode that detect the buildup of the titrant after the given endpoint or after the endpoint. Okay. Now, this is more applicable compared to the other one, yung tinatawag na amperostatic. This is more applicable than potentiostatic. Okay, amperostatic, if you're going to look at this, the root word there's current. If it's potentiostatic, that's the root word there is mostly the potential, the voltage. Okay, so you can use it for acid-base titration. Okay, water to generate your hydroxide or water to generate your H+. Okay. And then you can use this also for complex titration with EDTA, and commonly in the so-called redox titration. So these are just where you apply this amperostatic titration or colorimetric titration. Now, if we're going to compare this thing with the typical titration that we have, we could say there's some common denominator on them. Okay, so there's what we call the current, which is electron generation. So it serves as the function of the titrant solution. And then time, you can use time as a function of the volume that is delivered, especially if it's an automatic. There's usually a device for this, commercially available. Okay, and then the amount of the analyte is determined by combining capacity. Now, the thing that you need is, as much as possible, like most of the titration reaction, you can have a rapid analysis and essentially complete and free of side reaction. Now, the advantage of this colorimetry, okay, compared to this typical titration, both time and current is easy to measure to a high accuracy. So they're more accurate, okay? And you don't have to worry about the titrant stability, especially if you have the commercially one use, okay? So it's easier and more accurate for smaller quantities of the reagent. So you can use small volumes of dilute solution, and that's really a very big problem for titration, the typical titration. And you can use it either for precipitation, complex formation, redox, or acid-base neutralization reaction. And this is one that makes it really great. Okay? It is readily automated. Okay. Now the sources of error is, as I've told you, this current. It should be as much possible stable during the electrolysis, because it could lead to departure from 100% current efficiency. And there could be error in the measurement of current and error in measurement of the time. And you also always have here the titration error, the difference between the equivalence point and endpoint. Okay. Now, in the change in the potential during these amperostatics methods, usually, as much as possible, you want a constant current system. Okay, kaya natin tawag na amperostatic. So that means constant current. Now, sometimes the potential of the cell will vary with time as the analyte is consumed. Okay. So what happened here, the cell would seeks out the electrochemical reaction capable of carrying the supplied current. So let's say initially ito yung initial reaction mo, but when we have the Nernst equation, you know, Nernst equation usually depends on what? The activity or the concentration of the ions that are involved. Okay? So, ang mangyayari niyan, pwedeng maapektuhan yung reading mo. So in instance, the potential of the cathode depends on the activity of your copper 2+. Now, as the copper 2+ decreases, it results to deposited by the reaction or deposition. So what happened? Your the potential of your cathode would decrease. Okay. So here, if you're going to look at this, so usually mag-ano sila ng equilibrium potential, they establish it. But after some time, okay, nagbago yung potential, pwedeng magbago yung current na magre-result sa iyo. So that's one of the problem that you have if the potential is changed during the amperostatic method. So when all of this copper is consumed, the current is carried out by another electrochemical reaction. So either mag-generate ka ng H+ or hydrogen from the H+, or there's a breakdown of water if oxidation happen. Okay. Now, this is not a problem as long as the other species don't co-deposit. So if you have a large excess of species being used in a titrant generation versus the titrated analyte, like silver reacting with the chloride in solution. Okay. Now, punta naman tayo doon sa potentiostatic. Okay, compared doon sa diniscuss natin na emperostatic. So here, we could say that the potential is the one that is constant. So the detection of the analyte in solution by using colorimetry at fixed potential to quantitatively convert the analyte to a given form. So the current here is what we call controlled by currents of the cell. So you might see this setup: counter electrode, which is your indicator electrode, the reference electrode, and the working electrode. Okay, so there's an advantage of this compared to, let's say, the amperostatic one. It's more specific. Okay, because it avoids the redox of species that may interfere with amperostatic colorimetry. And they have been used for over 55 elements without major references. Okay, the disadvantage that you have, it does take longer than amperostatic titration. Okay, and the current would decreases with time. So nababa yung current with time, and the conversion becomes slower as less analyte around to oxidize or reduce. Okay, so ito yung usually formula na ginagamit nila dito sa type na tinatawag nating colorimetry. So that's all I know. I don't have any experience yet on this what we call method. So may tanong? May tanong? Now, among the three, I would say this is the one that I'm a little bit familiar, but unfortunately, this is also has the most numerous electrochemical methods. Okay, and I think I'll just discuss some of the basic because time will not allow us to discuss. So ito yung tinatawag nating voltammetry or yung voltammetric method. So how is voltammetry in comparison doon sa na-discuss na natin? So here, this is an electrochemical method in which the information about the analyte is measured in terms of current as a function of applied potential. Okay, and what makes this useful because you only need to use a small amount of sample. So, yung classic instrumentation niya, meron kang working electrode, reference electrode, at your counter electrode. At lahat yan nakadip doon sa supporting electrolyte. So, ganito yung parang symbol niya. Okay, so yung counter electrode, that's your indicator electrode. It can be mercury or platinum. Okay, yung working electrode mo, yan yung micro electrode whose potential na nagbabari with time. You can fabricate a working electrode, okay, but it must be used with a reference electrode, and usually the one that in my experience, I prefer to use the silver chloride electrode compared to the Columnal because that's the one that I have available during that time. So, sa reference electrode, the potential would always remain constant. Okay, so the counter electrode, indicator electrode, told you mercury or platinum, it completes the circuit and it conducts the electron probe signal source through the solution to the working electrode. And all of these three okay, will be put in a cell that contains your supporting electrolyte. So that's an excess of non-reactive electrolyte or alkali metal to conduct the current. Now, if you're going to look at what is happening here, so maybe with time, you can increase the potential, and this increase in the potential would also result in changes in terms of the current. Okay, so if you apply linearly the potential with time, you increase the potential with longer time. So the corresponding changes in the current looks like this one. Okay, so how is this different from potentiometry? So when we look at the potentiometry, it measures your potential at near zero current. Voltammetry measure current as a change in potential. So si change mo yung potential, titignan mo yung corresponding change ng current. Columnmetry, it uses up the analyte in the process of measurement at fixed current or potential. Voltammetry, you only use small amount of analyte. So kailangan mo lang yung maliit na sample. That's why this is very popular. Okay? Now, believe it or not, this is a Nobel Prize winner method. So a Czech chemist, Jaroslav Hebrovsky, first reported voltammetry, but at that time it is known as polarography. And I think he won the Nobel Prize sometimes during the 1950s. Okay, so if you're going to look at the theory of voltammetry, babalik ulit tayo doon sa naano natin. I don't know if you were able to follow the changes that you have here. So you have an excitation source. So the potential is set by the instrument. So doon mo yan i-set sa working electrode. And what happened? You establish the concentration of the reduced and the oxidized species at the electrode based on the Nernst equation. So usually the reaction happens at the surface of the electrode. So if you have Fe3 plus there, it can be reduced to give you Fe2 plus. So for instance, okay, you try to monitor the concentration of your Fe3 plus in the bulk concentration, you apply the potential. So what will happen? Do you follow the changes that you have here? So with increasing time, makikita mo yung changes doon sa bulk concentration. Okay? So yun yung nangyayari doon sa surface, the electron surface. And the condition of the current that we have here, okay, we can measure the rate at which the species can be brought to electron surface. And there's two ways to do that. Either you do it using stirring or unstirred. So if you use it with stirred, meron tayong tinatawag na hydrodynamic voltammetry. If it's unstirred, we have this classic polarography. Okay? Yung tinatawag na hanging mercury drop electrode, HMDE. That's the dropping mercury electrode. So if we're going to look at this electrode, okay? So ito yung electrode niya, tapos meron siyang parang diffusion layer of the solution. Tapos meron kang laminar flow, tapos ito yung bulk solution. So ito yung interface. And this is not new to you, right? Yung introduce ko yung method last time. So you can have migration, convection, and diffusion. So migration has something to do with movement of ions, okay, in the solution through electrostatic attraction to the charged electrode. Convection has something to do with mechanical, okay, and then diffusion has something to do with gradient in the concentration. So makikita mo rin yan dito. I think the main reason why I discuss it there is because of this what we call method. Okay, So tinitingnan nila ano yung nangyayari doon sa bulk solution tsaka doon sa electrode surface. So dyan nangyayari yung mga changes. So if you're going to look at the voltammetric analysis here, so this is another way to represent. So this is your indicator electrode. This is your reference. Oh wait, this is the working electrode, okay? This is the reference and this is the indicator electrode. So if you're going to look at here, yung 0.1 molar KCl mo, yun yung supporting electrolyte. And you're trying to determine the amount of lead 2 plus in the solution. Okay? So what happened there? Madidetermine mo yung lead 2 plus by providing the applied potential on the working electrode. What does it mean? A certain analyte would have a certain potential wherein yung Pb2 plus mo mako-convert sa Pb. Okay? So the electroactive species in the sample solution are drawn towards the working electrode where a half cell reaction takes place. So dito magkakaroon ng changes. So from Pb2 plus, magiging Pb. And then in addition, another half cell reaction will also take place at the counter electrode. So what's happened here? So maybe your K plus here is converted to K. Okay, and the resultant current flowing through the electrochemical species would reflect the activity. So anong ibig sabihin niyan? The more ions you have there in the sample solution, the greater would be the signal that it will generate. So if you're going to look at this, at what's happening, so these are the solutions that you have there. So what happened? Okay. So maybe this is what is happening. I hope you see the changes that happened there. So in nung reference electrode, yung K plus pumunta doon sa surface. So there's a layers of K plus that is built up around the electrode, which stops the migration of your Pb2 plus via the Coulombic attraction. And you will develop this concentration gradient, okay, between the surrounding of the electrode and the black box solution. So once you develop that, your Pb2 plus will migrate via the electrode through diffusion. Yun yung concentration changes. At dahil doon, magkakaroon na ng signal that corresponds to that. Okay? So ganito yung nangyayari doon sa electrode surface. And if we're going to continue, what happened there? Yung MOX more oxidized form. So usually that's the charged form, right? Like M2 plus. Okay? So kapag in-add mo yun ng electrode, magpupunta ka sa redox. I'm just trying to make sure. No, this is the what we call 2 plus and then Pb. Oh, this is the reduction form. Okay. So if you're going to look at this one, the oxidized form, pasensya na maingay sa background. Okay, it will be with the addition of this what we call electron, it will be in the reduction form. Okay, and you're going to look at the changes that you have here at the surface of the electrode, and you will be able to get the applied potential. So yun yung kailangan mo malaman, anong potential yung gagamitin mo para ma-observe yung changes doon sa current. So I don't know if you see the changes here, the electrode, then after 1 second, after 2 seconds, after 5 seconds, nakikita niyo yung pagbabago. Okay? And if we apply the potential, we want to make sure that it is higher than what we set. So we can either use a stirred solution para maano yung convection na mechanism. Okay? And when that happens, makikita mo yung changes doon sa current when the potential increases. So the current generated at the electrode by this process is usually proportional to the concentration at the surface, which in turn is equal to the bulk concentration. So yun yung basis ng tinatawag nating mga voltammetric method. So the more ions that you have there, okay, kapag in-apply mo yung potential where the ions is converted into reduced form, so the better is the signal that you will get. So ito yung parang current equals to the number of electrons in the half cell reaction times Faraday constant, okay, times the electrode area times the diffusion coefficient of the A, which is the oxidant, and then multiply it with this thing here, the slope of the curve between the concentration of the oxidized form and the concentration of the oxidized form in bulk solution and the concentration of the metal in oxidized form in your surface. And ang nangyayari dito, as time would increases, it push bonding further and further out, and it results in the decreasing current until with time, until it reached the point where convection of analytes takes over and diffusion is no longer a rate limiting process. So makikita mo merong diffusion, and then after some time magiging convection. So what do they do here? Okay, they can consider the thickness of the diffusion layer, and based on this concept that they have, they said that the current is proportional to the bulk concentration, because you're trying to develop a method wherein you relate the amount or the concentration of a certain ion, which in this case metal ion, doon sa current. So kapag in-stir daw yung solution, nagdi-decrease yung thickness ng diffusion layer. Okay? And in that case, since nagdi-decrease yung diffusion layer doon, yung thickness niya, magiging mataas na yung current. Kasi yung diffusion layer, the thicker it is, mas mahirap maka-interact yung bulk solution doon sa surface ng electrode. And if you're going to look what's happening here, as you apply the potential of the working electrode, you usually sweep it or scan it, okay, from the lowest to highest potential or highest to lowest potential. So if you're going to look at this, you sweep mo yung potential na yan. Okay, so here, what does it mean here? At this potential, yung working electrode mo, hindi niya kayang i-reduce yung CD2+. And then you continue on sweeping it, and then all of a sudden, tumaas. Okay, so what does it mean here? This potential is the one that you can use wherein you can convert your CD2+. So at this, what we call potential, all CD2+ around the electrode has already been reduced. And the current at the electrode becomes limited by the diffusion of CD2+ from the bulk solution to the electrode. Kasi, ano na nangyari doon sa CD2+ mo? Na-convert na siya sa CD. And when na-convert na siya sa CD, yung diffusion yung CD2+ from the bulk solution sa electrode na decrease na. Kasi meron ng naharang na CD. Remember, this is the solid form. And in this case, your current will stop from rising. So kapag linear sweep yan, ganito yung itsura. But in other, okay, they just do it like that. If you're going to look at some other, what we call literature on this one. So ito yung tinatawag na linear sweep voltammetry. So you just try to sweep at the different potential kung saan, okay, mag-undergo ng change yung metal mo. Okay, so that's the potential, the half potential that you have here, and this is, we could say, the baseline of the residual current. Okay, And if you're going to combine both the potential and the current together, this is what you will get, how it looks like. So this is if you have voltammograms of mixture. So ibig sabihin may dalawang species ka doon. And usually these two species, they would have different what? Potential. So makikita mo, yung isa, okay, tataas yung current at a certain potential, and that's different from that one. Or you can also have different concentration, okay, that results in different current but the same potential. So what does this mean? Okay, you could say that they're just the same species of different concentration. Now, yung basis nung sa sugar meter na meron tayo, it is something to do with amperometry. So you can also use an amperometric titration. So here you measure the equivalence point if the analyte or reagent are oxidized or reduced at working electrode. And the current is measured at peaks potential. So ito yung difference, yung voltammetry current at changing potential. And here, if it's a titration, current measured the peaks potential as a function of the reagent volume. So the endpoint here is intersection of both lines. So like this. So the volume of reagent. So here only the analyte is reduced. When it reaches here, only the reagent is reduced. And then if you look at the interaction here, both the analyte and the reagent is what we call reduced. Now, you can also use like pulse. Ano ibig sabihin ng pulse? Di ba yung pulse taas tapos baba, taas tapos baba. So the way that you're going to do it, you apply the potential. Okay? So instead of linear, pag pulse, tataas mo tapos bababa. Okay? So taas, certain time, then baba, taas, and then baba. Okay? So instead of linear change of the potential that is applied with time, you can use step changes or pulses in the potential that is applied with time. And here you measure two currents at each cycle. Okay? So yung common method na ginagamit nila dito ay yung differential pulse potentiometry. So what it do, okay? So yung initial time mo, this is before pulse. Tapos yung estimate mo, that's after the pulse, at the end of the pulse. And then the way that they do is they look at the changes in the current dito, okay? With respect to the potential that they applied. And they found out that the peak height is directly proportional to the concentration. So ito yung common na makikita mo na ganito yung lalabas. So the advantage of this is can detect the peak maxima differing as little as 0.04 to 0.05. And a 0.2 volts peak separation is used for normal voltammetry. And the good thing at this, it can go as low as 10 to the negative 7 to 10 to the negative 8 molar. Okay. Now, the one that we commonly use, if you want, let's say, to characterize the redox potential, yun yung tinatawag na cyclic voltammetry. What does it do? Okay. You ramp up the potential and then reverse it. And what you're going to look at here is just look at the redox window. So tinitingnan mo saan yung reduction at saan yung oxidation na nagpo-form. And usually a typical CB would look like this. Anong hayop ang naalala nyo kapag may ganito? Anyone? I don't know if you agree with me. It's a duck-shaped thing. So what does this tells us? This tells us that if you ramp your potential, okay? So let's say from highest to lowest here. Because iba yung conventional yung European tsaka yung American. So yung iba dito yung negative to positive. Yung iba dito yung positive pupunta doon sa negative. But what it do, okay? if you have this what we call cyclic voltammogram, so ibig sabihin reversible yung redox reaction nila. Because you can also have it like this. Dito lang mataas, tapos pagbalik sa ano, straight line na. So ibig sabihin, ito lang yung either nare-reduce or ni-oxidize na species. Okay? So if you're going to look at what is happening here, so you have an initial negative current due to the oxidation of water to give oxygen. And then, wala siyang current kasi constant. Okay? And then at 0.4 voltage, the current begins because of this reaction. So there's a rapid decrease down dahil nga doon sa surface mo na ang nangyari, bumaba yung concentration ng ferrocyanide mo. And then you obtain the so-called peak potential, cathodic peak potential. And then all of a sudden magdi-decay kasi yung diffusion layer mo is extended further from the electrode surface. So nag-form na yung species na to. Okay? And then the scan direction would switch back. So the potential is still negative enough to cause the reduction of your FeCN3+. And what happened, eventually, yung reduction ng FeCN was no longer occurs, and what happened is the reverse reaction, the reoxidation of this to become like that one. Then you have the anodic peak potential. And then the current would decrease as the accumulated FeCN6 4- is already used up. So this is really useful. When I work with mom lab, this is what we try to look for changes because it will tell us yung tinatawag nating reduction potential window ng system. Now, the only thing that you know is you have to know what are the species that is present para makorelate mo yun. There's calculation for this one, but hindi ko na kayo, I will not ask for any calculation. If you want to determine this cathodic and anodic peak that you have. But the important thing that you can get there is you can calculate the standard potential for the half reaction. You can determine the number of electrons that's involved in half reaction. You can determine the diffusion coefficient. Okay? And you can determine if the reaction is reversible. So kapag makikita mo yung duck shape, you could say it's reversible. Pero pag nakikita mo lang isang peak lang, like that one, or we could say straight dito tapos bababa dito, then that means it's only, we could say, a one direction reaction. And I think that's it. Tapos na tayo. That's the last slide. I hope you learned something. I know it's just too much of information. And to tell you frankly, some students spend the whole time in their PhD just studying one part of that. When I left the Philippines in 2005, I'm an electrochemist. But when I came here, and the professor told me, oh, do you know Victoria Beckett? And then I look at, kilala niyo yun, ma'am? Sabi ko, hala, 1976 siya natapos ng PhD. Sabi ko, kapapanganak ko lang. Because he was already, I think, in Australia during that time. Advice daw niya yun, sabi nung professor namin sa electrochemistry. And the professor during that time, that's 2005, was already 85 years old. So sabi ko, hindi ko ata kaya to. So nagbago yung ano ko, yung specialization ko. And even Dr. Aga said, huwag ka dun, walang pera yun. Baka hindi ka graduate. And all of a sudden, wala, nag-shift yung career ko. Because if you watch the 230 video that we have there, what I did there with my students in UPLB, we developed these working electrodes. And you know what we have? This copper wire that we polish. And then, alam niyo yung straw ng Tetra Pak? So I don't know how my students get a supply of that. So we put the yung copper wire doon sa loob ng yung straw ng Tetra Pak, and at the end we have this carbon powder. Okay, we can buy it. We mix it with an oil, and then we put it with some waste material that we know has some functional group that can bind with the heavy metals. At yun yung thesis nila. Okay? They optimize the ano yung magandang supporting electrolyte, ano yung potential na magagamitin, ano yung deposition potential, ano yung accumulation time, ano yung pH. And then when they develop the electrode, I asked them, okay, you get the reading using the optimized condition and compare the metal content with the AAS. Yun yung ano namin. Because sabi ko, you'll be happy if it's the same, but I expect it to be different because the mechanism that they have is usually what we call different. But some said, oh, it's close because we use this standard addition. So we look at the increment in the changes of this concentration. And then we said, oh, I think we can work this out. So yun yung, I think I have 20 plus students who graduate their BS thesis using those theses. One of them even telling me, nakakasuka naman po yung title natin. Parang optimization of carbon-based electrode using, kasi ang alam namin, ang tawag namin yung Potentiometry. Tapos, basta trode kami yung tawag sa mga, so anong ginagawa mo? Pinya po, tapos yung isa banana trode, kasi nagawa siya ng banana. We're taking advantage doon sa enzyme, di ba? Yung banana, pag iniwan mo, nagba-brown. So sabi namin, oh, that could bind with metal. Tapos yung isa pinya, yung, kasi sabi namin, di ba, when we use it with, I don't know if you know the science why we use it with the meat. So usually there's some enzymes that tenderize the meat. Sabi namin, sige, gawin mo yun. Tapos meron pa kaming feather trode. The feather chicken, which I presented in a convention in animal science. Nagkagulo sila. Yung tanong, alam yung tanong sa akin, yung bang feather nung manok na pula ay iba doon sa manok na puti? Hindi ko rin alam masagot. Sabi ko, basta may keratin yun. Yun lang yung inaano namin. That's the only one. Nagkagulo yung yung nag-attend, nung nag-present namin doon. Those are the time that I have when I was starting my career. And I was really happy yung sabi namin, oh, nakagraduate yung 20 plus student na nag-BSTC sa akin. And it happens because, I don't know if you know, Dr. Joey Santos left. So I said, oh, there's an instrument. Baka naman pwede natin gamitin to. Kasi sayang naman. Okay? And I'm not sure if it's still functional at this time. But I can tell you, you can have a career out of this electrochemistry. It just changed, I mean, my perspective when I arrived here. I said, I don't want to work with this because naisip ko, baka lumampas yung 5 years, hindi pa ako tapos ng PhD. So that's the one that changed me from being an electrochemist to at least naging analytical chemistry pa naman. And that's how I said, oh, I know all the big three, one way or another. I have experience with them. It's just that the electrochem is the one where I really have what we call develop myself. Tapos napunta nga ako sa chromatography, and now I'm more on spectroscopy. So question. Yung application usually ng voltammetry is for environmental analysis of the metal. So yung tinatawag na stripping analysis. And ma'am, meron akong maliit when I was working with ma'am. Too bad it's too late. Naghahanap si ma'am noon. So a common friend of us, the late Alonso Gabriel, he was able to get money. Pero alam ko yung main ano niya is he wants to go to the state. That's why he might collaborate with me. So he can go to New York from time to time. So in the funding that we have, we're able to buy a portable one. So if I will be able to go there this summer, I'm going to bring yung parang kasing laki lang yung case niya nung laptop. And then all you need to do is parang ganito lang kalaki yung yung system, tapos i-connect na natin. tapos i-ano mo lang yung alligator chip. I think, I don't know if you know Sir Franco. That's his specialization. Yeah, when I went there, because he taught me again how to do the electrochemistry. Kasi iba na. Kasi yung time namin talagang medyo malaki yung tawag namin electrochemical cell. But during that time, they just do it like in a strip, in a very thin strip. So ganun yung ano ngayon, ang ano nga nila is doing it rapidly and on-site. Even the Raman, they said, oh, because I'm also active in our forensic science program, being the assistant director. So inaano ako ng director, oh, mag-abang-abang ka. Minsan, pinamimigay na lang nung DEA, Drug Enforcement Agency, yung mga equipment nila. I have there in the lab 4 ATR. Sabi nga namin, kanya-kanya na tayo. Ang ano nga namin, sabi ko nga, pwede ko bang isend to? No, wag, magkagalit sa atin yung DEA. Yun yung PIDEA version namin dito. Kasi nakaano sa atin yan. Pag nalaman niyang inaano, baka hindi na tayo bigyan. But we still have our what we call Spectronic 20. The ever reliable Spectronic 20. Yun yung, I said, sabi, pag biochemist ka, ang number 1 na kailangan mo is a pH meter. Pag analytical chemist ka, ang number 1 na kailangan mo yung balance. Pag wala ka doon sa lab, magreklamo ka doon sa manager mo. So question class.
May mga how much yung portable CV?
Nakuha namin nung kay Al ng 7 I think they gave me $10K. Okay. Hindi pa nga namin na-install kasi nung mag-i-install na nag-pandemic. we got it December, I think 2 years na. Nung pandemic nga, inuwi ko dito sa bahay. Kaya ano nga ngayon, inaano ako ni Arvin. Sabi niya, sir, pwede ba kayo mag-develop sa metal? Doon sa mga niya, yung ano ba tawag, non-traditional, yung parang alternative sa rice. Sabi ko, oh, sabi, tapos nag-chat kami, eto, ang may-ari nito, Pilipinas. Because from UP Diliman. Pero sabi ko, duda ko rin kung gagamitin nila kasi wala na si Al. Sabi ko, pag hindi ko rin ibabalik sa kanila.
So pag uwi mo ng August 2020, July-August 2022, bibitin mo siya.
Bibitin ko po. Baka nga nakalimutan na nila doon sa Diliman
Huwag mo nang banggitin.
Yun na nga. Kasi hindi naman, kasi sabi ko nga hindi talaga yung Chem. So baka ang niyan, hindi na rin nila gagamitin. It's a very good, and I still have the benchtop na nag-aano doon. Ang problema nga sa amin, I'm more on ngayon sa spectroscopy. So parang kasi hindi mo kaya at the same time lahat Even within spectroscopy, may pa yan. So you know that there's an absorbance, there's a fluorescence, and then there's the vibration of spectroscopy. So hindi mo pa rin yung field. And the thing when you do your specialization like an MS or a PhD, your field will be narrow. Sometimes konti lang yung kilala nyo. I remember one of my Filipino students here at Pace University. He went to Michigan. Hindi niya tinapos yung PhD kasi sabi niya yung slab spectroscopy. Sabi ko, ano yun? Yung parang inaano nila yung angle tapos sabi ko masyadong specialized yan. Pagka-graduate mo, walang kukuha sa'yo. Kasi konti lang yung ginagawa. Kasi ang nangyayari kasi, if you go PhD, your knowledge, yung specialty mo, talagang lumiliit. Feeling mo, may alam pa ba ako sa Chem? That's just based on my experience. That's why it's advisable for you to do postdoc. para at least maano yung and my advice if you do postdoc, wag naman yung specialization mo nung PhD mo. Because I was lucky during my PhD, Dr. Aga said, wag ka na doon sa electrochem. Sabi niya, ang sabi ko, kung hindi ho ako sa electrochem, meron ho akong target na professor. I don't know, ma'am, you know, Frank Bright, nung nandoon kayo sa UB. So si Frank Bright.
Sa UB, okay. Hindi ko siya kilala, pero saan lab siya? Chem siya?
Chem din po siya. Sa ano siya, 1 floor below nung Aga lab. Kaya meron akong room sa both lab eh. Sa Aga lab wala kasing bintana sa labas. So hindi namin alam, hindi natin alam, naglalab tayo, nag-i-snow na sa labas. Eh doon sa Bright Lab, tabing ako, window. So minsan, nakatungangala ako, nag-i-snow na. So his specialization is more on material science, yung sol gel, and spectroscopy, especially yung laser. Yung meron kaming lifetime, fluorescence, saka steady state. And then sabi Doc Aga, sige, i-combine mo. So I said, okay. So ang ano ko kay Doc Aga is environmental na mass spec. And then sabi ko, dagdag ako, kumuha pa ako ng computational. So sabi ko nga Bright, Aga, and Ochbach. Sabi ko, ABA, ABA. So ang iba-ibang field because I was preparing myself to go back. Kasi wala akong analytical chemistry during that time. I think it's just Dr. Pajardo, tapos hindi pa talaga siya analytical chemistry. But hindi ko nakabalik doon. So when I went to my postdoc, which is with another Filipino, ang napuntahan ko naman specialization is vibrational spectroscopy, yung IR, tsaka Raman. So kaya parang naging yung field ko. So one way or another, I experienced the big three. Or if you consider mass spec, that's the big four. And I think it's really helpful to me. So I said, about that, so ganito. But unfortunately, medyo nahuli, and since matagal na ako dito, yung naiwanan talaga yung electrochem. So when I went back to work with Dr. Migo, I said, I have to review what I learned from before. Yun yung parang why I end up in analytical chemistry. So, ipopost ko yung PowerPoint, ipopost ko rin, meron akong nakitang mas simple explanation, like this one, kaya tatanggalin ko na yung background. Nawala. So, it's a PDF file. Nawala yung background ko. So, parang ganito, analytic introduction to the electrochemical, because I think this is the simplest explanation na nakita ko, which I just what we found this morning, and I was already supposed to make a PowerPoint of it, and all of a sudden at 5 o'clock I said, we have a meeting. Iniisip ko Tuesday dito yung meeting, yung pala Tuesday dyan. So sabi ko, okay. So that's all. So next meeting, yung last meeting natin, it's the radiochemical methods and the particle size methods. So these are new. I think the radiochemicals is old, but the particle size is a much newer thing. It was developed maybe pagka-graduate na ako because of the studies on nanotechnology, because that's one field that is really in demand. Sabi nga nila, if you're going to look at literature, I think when you say nanomaterial, that's the number one. And if you go on that field, okay, hindi ka pwedeng mapag-iwan kasi their publication, there's really high. The rate of publication is high if you are in nanotechnology, which I think is being done there. Si Lia po, di po ma'am? Ano siya, nano? Yeah. Kasi yun yung in demand ngayon. Yun yung parang field na ano nila. So question, I know we're over time.
May mga umalis na nga, baka may klase ng 1.
Anyway, we have our what we call recording. So tingnan nyo na lang, and the reading material. Okay?
Okay.
So one more meeting. And just follow yung schedule na binigay ko, in-email ko. We will follow that. Okay? So okay na daw yung kaso nyo kasi chika-chika muna. Pero hindi pa rin kayo makathesis. Yun yung sabi nung taga-UP Diliman. Which is sad. Nagtitesis na po ba mga to?
Hindi pa.
Anong year
Bali,
level nyo na?